Hi everyone, my name is Shreyas and I'll be talking about design of connectivity-oriented pheromone-based mobility model for UAV swarms. My advisors are Dr. Sunil Kumar and Dr. Alexander Eiler, and our work is supported by the US Air Force Research Laboratory. In recent years, there's been a surge in the use of inexpensive micro-UAV swarms for civilian and military applications such as search and rescue, surveillance and tracking, and also has loitering ammunitions. Therefore, there is a need to develop scalable, decentralized autonomous UAV swarm architectures with high network connectivity. In our work, we look at developing a connectivity-oriented, pheromone-based mobility model for search and rescue operations that is capable of maintaining high network connectivity. In our scheme, we use technology-based digital pheromone maps along with local connectivity information to achieve efficient coverage while maintaining high network connectivity. High network connectivity facilitates the spread of digital pheromone maps and connectivity information throughout the swarm in order to coordinate the swarm and transmit data among the nodes. Here, the UAVs deposit repel pheromone in already scanned sectors of the map to promote coverage, and UAVs select the next waypoint based on the repel pheromone value and the estimated connectivity at the waypoints. However, one of the challenges of the scheme is that the coverage and connectivity performance of the UAV are inversely related. As seen in the diagram on the right, we see that the waypoint on the right has low pheromone value but also has low connectivity, whereas the waypoint in the middle has high pheromone value but high connectivity. But this gives bad coverage. So we need to select a waypoint that is able to give us good coverage as well as good connectivity. Here we go into some more details of our heuristic scheme. The connectivity between two nodes is calculated as a function of the Euclidean distance and the transmission range. We chose this definition for connectivity as two nodes closer to each other have better link quality and are more likely to stay connected for a longer duration. Likely, distance-weighted degree of connectivity denoted by Ki gives how well a node is connected in the network. The next waypoint selection depends on Ki and the pheromone values. The UAV selects the next waypoint with the maximum Pi value. Pi is denoted as seen here. Alpha I depends on Ki. Here, less weight is given to pheromone values at waypoints that does not favor connectivity. Here we compare our heuristic model with the pheromone model. In the simulation, we've used 30 nodes with a UAV speed of 20 meters per second in a map of 6 by 6 kilometers divided into 60 into 60 grid cells. In terms of coverage, we look at coverage versus time plots. Here we see that the heuristic model does not perform as well as the pheromone model and takes 200 seconds longer to cover 90% of the map as compared to the pheromone model. But in terms of connectivity, we see that the heuristic model performs better. The number of connected components decreases by 54% and the average network connectivity of the heuristic model increases by 96%. Next, we look into using Q-learning to find a mobility model for UAV swarms that gives the best trade-off between coverage and connectivity performance. We have extended the single-agent Q-learning algorithm to the multi-agent UAV swarm scenario. Currently, we are using discretized state and action space. One of the challenges of using discrete state space is selecting a discretization step size for the pheromone and connectivity values. If the step size is too small, the state space increases and the training becomes very hard. With these limitations of using the discretized state space, currently we have achieved comparable performance to the heuristic model and are looking into ways of improving it further. For future work, we will be looking into continuous state space to use deep Q-learning. Thank you.